started on our next unit. This is just more stuff with triangles, kind of a couple different things. We're going to start with perpendicular bisectors and medians of triangles. And this is a section that doesn't really fit anywhere else. So we're just doing it right here because it doesn't really go with any of our other sections. But then we'll spend a few days on triangle similarity. We've done triangle congruence, but now we'll do similarity and get into what that means. And then we'll finish up with medians and, not medians, mid-segments and what we call the side splitter theorem. So that'll be loads of fun. So just a few random things thrown together about triangles for this unit. Recall that, let's go ahead and jump into section 1. Recall that a perpendicular bisector splits a line segment into two congruent segments and creates a right angle. We haven't talked about perpendicular bisectors since the beginning of the course. They've shown up every once in a while, but not very often. So the perpendicular part says we create a right angle, and the bisector part says we split it into two congruent segments. If a point is the same distance from two other points, it's just a vocabulary word, we say it is equidistant. So if you see the word equidistant, it's exactly what it sounds like it should be, equal distance. It's the same distance from both things. Not necessarily right in the middle, but it's the same distance from both. Now the perpendicular bisector theorem tells us that in a plane, which just means we're on a flat surface, if a point is on the perpendicular bisector, then it is equidistant from the endpoints of that segment. So looking at this picture here, what that means is any point on that line, CP, is going to be equidistant from A and B. So I could draw an infinite number of triangles here, or an infinite number of line segments, and those two are going to be congruent. The two that were originally drawn in, AC and BC, those are congruent. I guess I should put 3 on there. If we wanted to keep going down here, okay, we could do any number of points on that perpendicular bisector. They're always going to, that point will always be equidistant from points A and B. So if we know it's a perpendicular bisector, we know that we have, in this first example, it actually looks like two sides of a triangle that are congruent. It's not always a triangle, but oftentimes it looks like one. So if we know that BD is a perpendicular bisector, and I just abbreviate that. Upside down T is the symbol for perpendicular, remember that, and then BIS for bisector. So if that's a bisector, we know that AD is going to be congruent to CD. And what do we do with congruent things? We set them equal to each other. So 8x minus 4 equals 3x plus 1. Let's get all our x's on the left side, so we'll subtract 3x from both sides. That'll give us 5x minus 4 equals 1. We'll get rid of the minus 4, so we'll add 4 to both sides. 5x equals 5. Divide both sides by 5. So x equals 1. That's not what we were asked to find, though. We were told to find CD. So let's go back and plug that in. CD is 3x minus 1. So that will be 3 times 1. Plus 1, not minus 1. So that will be 3 plus 1. So CD equals 4. On part B, we know that BD or ED or DB or DE or BE, there's too many ways, there's several ways to name it. We know that that vertical line is a perpendicular bisector. We know that because these two pieces are congruent and we have a right angle. Remember that. That's what makes it a perpendicular bisector. Because it is, we know that AD and CD are congruent, just like in our last example. So what do we do with congruent things? We set them equal to each other. 5x minus 20 equals 2x plus 4. And just like last time, we will solve for x. And in this one, we're still finding CD. So let's subtract 2x from both sides. So that will give us 3x minus 20 equals 4. Add 20 to both sides, so 3x equals 24. Divide by 3, so x equals 8. CD equals 2 times 8 plus 4. So that will be 16 plus 4. So CD is 20. Now, if we wanted to check to make sure we were right, we could plug it into the other side also, because they should be the same. So 5 times 8 minus 20, that's 40 minus 20. So we get AD is equal to 20 also. So we can be pretty confident that we did it correctly because we got the same thing on both sides. Now, the converse of the perpendicular bisector theorem is also true. Remember, converse means we turn it around backwards, and it says if a point is equidistant from the endpoints of a line segment, it is on the perpendicular bisector. So this is saying that if AD and BD are congruent, if these two are congruent, then D is on line CP, because CP is the perpendicular bisector. And the thing is, when we work these, we really work them about the same, only now we're dealing, in the example for example 2, now we're dealing with the original line segment versus the diagonal ones. So we see that CB and AB are congruent, and that means that this is a perpendicular bisector. So BD is perpendicular bisector of AC. And that means AD and DC are congruent because that line segment is bisected. It's split into two congruent pieces. And we work it just the same way. They're congruent, so we set them equal to each other. 4x equals 2x plus 4. Subtract 2x from both sides. Divide by 2. So x equals 2. We're still finding CD. So that's 2 times 2 plus 4. So CD is 4 plus 4, so it's 8. And again, if we wanted to check, we could check for this one, 4 times 2. Well, hey, that's 8 also. So we know we did it correctly. So perpendicular bisector theorem, if a point is on the perpendicular bisector, it's equidistant from the endpoints. The converse is, if it's equidistant from the endpoints, the point is on the perpendicular bisector. And again, we work them the same way for the most part. Let's go on to medians. Actually, before we get to that, another vocabulary word. When 3 or more lines intersect at one point, they are concurrent. Concurrent. That means they all meet at the same place. And that point where they meet is called the point of concurrency, and that will matter here in just a moment. So the median of a triangle, or medians, because every triangle has 3 medians, they are formed by connecting a vertex to the midpoint of the other side. So if we look at point A in this triangle, AE is a median because BE and EC are congruent. So we know E is the midpoint, E is a midpoint, so that's what makes AE the median. And all three of your medians in a triangle will meet at a specific point. This is called the centroid. And the centroid is known as the balancing point for a triangle. So if you were to have kind of a three-dimensional representation of this triangle, and you put point P on your finger, you would be able to balance the triangle. Would not, I mean, it depends on how steady your hand is, but the weight of the triangle itself would not make it fall over as long as you keep your hand steady. Now, the centroid is always 2/3 of the distance from the vertex to the midpoint on the opposite side, which means that if FB were 9, okay, we're going to look at that one right there. If that whole thing is 9, then we know BP would be 6 and FP would be 3. So the part of that line on the vertex side, BP, is 2/3 of the whole length. The part of the line on the other side is 1/3 of the whole length. So if you know either the whole thing or either of the small pieces, you can figure out the others, which is actually what we're going to do here in just a moment. So in triangle RST, Q is the centroid, which means it is where the medians all meet. Find QW, that's that piece right there, and SW, which will be that whole thing there. So we know that QS equals 8, and that's 2/3 of the whole thing. So we know that 2/3, actually let me change colors. 2/3 of SW, the whole thing, equals 8, because QS is 8. Well, how do we get rid of that fraction? Now, there's a few different ways you could do this, but the easiest way to get rid of a fraction when it's multiplied by something is to multiply by its reciprocal. So if we multiply both sides by 3/2, on this side they're going to cancel out, so we just have SW. 8 times 3/2, you could write that 8 times 3 over 2. That's 24 over 2, so that's going to be 12. So SW equals 12. Now we know that QW is 1/3 of SW. So QW is 1/3 of 12. And you could look at that as 12 over 3 if you wanted to. But that's going to make QW 4. Now you don't have to find SW first. There are several different methods you could go through to figure out what SW and QW are. But this was just one way to do it. So when you have medians, they are divided into 2/3 of the segment and 1/3 of the segment. So they're not half and half. They are, one is twice as long as the other. 2/3 is twice 1/3. So that's it for this section. So make sure you look over your practice problems and understand this. This is going to be on the test, but we do not have a mastery check for this section. So make sure you do that practice. If you have questions, please come and ask. Good luck.